Good afternoon, everybody. My name is Thomas Müller. I am the Director of Applications Development for the AFM business at Bruker. I'd like to welcome you to this installment of our AFM webinar series. The presentation today is titled Exploring the Limits of Viscoelastic Phenomena with AFM-based Nanomechanics. This will be presented jointly today by Professor Ken Nakajima at Tokyo Institute of Technology and Dr. Beat Pittenger at Bruker. First, Ken will speak to his latest research, and then Beat will explain how this ties to our most recent technology developments. Now, before I introduce Ken and Beat, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar. If you have a question, please type it into the questions dialog box. We'll accumulate the questions, group them, and then answer them at the end of the prepared remarks. Quite often we have more questions than we can answer, then we will follow up by email as well. Also, if you'd like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within a week in the webinar section of the Bruker webpage. You will also get an email with this link. Finally, when you exit the webinar software, you'll be asked to take a brief survey. We'd very much appreciate it if you take the time to complete this, as it helps us pick the topics that are most important to you and to generally make this series better. So let me now introduce our two presenters, Ken and Beat. Our first presenter, Dr. Ken Nakajima, is a professor at Tokyo Institute of Technology. He completed his doctorate in applied physics at University of Tokyo in 1997, focusing on the development of scanning probe microscope techniques for polymeric materials. After a postdoc at Riken, he joined Tokyo Institute of Technology, focusing on rubber elasticity studies using AFM, which led him to AFM-based nanomechanics developments in 2008. Continuing his career as associate professor at Tohoku and then as professor at Tokyo Institute of Technology, he continued his focus on rubbers and thermoplastics and pioneered the development of AFM-based nano-rheology. Professor Nakajima is the recipient of numerous awards, including the Seri Young Scientist Incentive Award, the Bridgestone Young Scientist Incentive Award, the JSCM Most Accessed Paper Award, and the 11th Seri Best Presentation Award. He's the author of 135 papers with more than 2,500 citations. Our second presenter today is Dr. Beat Pittenger. He's a senior staff development scientist in the AFM unit of Bruker. Beat received his PhD in physics from the University of Washington, Seattle in 2000 and has worked with scanning probe microscopes for 25 years, building systems, developing techniques, and studying properties of materials at the nanoscale. His work includes more than 30 publications and 3 patents on various SPM techniques and applications. His interests span topics from interfacial melting of ice to mechanobiology of cells and tissues to the nanomechanics of polymers and composites. So with that, let me turn it over now to Ken to begin the presentation titled Exploring the Limits of Viscoelastic Phenomena with AFM-based Nanomechanics.
Thank you, Thomas, for the nice introduction. I'm Ken Nakajima from Tokyo Tech, Japan. For everybody, thank you very much for joining this webinar. Today I'm going to talk about the AFM nanomechanics for the polymeric viscoelastic contact. So now I start. Can you hear me? Okay. So nowadays nanomechanics is a worldwide fascinating the techniques to visualize some nanomechanical property of the polymeric materials, which can be performed using AFM. And especially for the Bruker users, we can use force volume mode or peak force QNM mode, like in this movie. And then the question is how you analyze this each force distance curves. For example, one possible way is use JKR Contanet Mechanics, although this is a theory for elastic contact. So this is not perfectly applicable to viscoelastic properties. But anyway, this JKR Contanet Mechanics is now available in Bruker software together with the conventional DMT contact mechanics. But I will not go into the detail of the calculation procedures, but you can check the Bruker the software by yourself. Anyway, the most important point is now this type of nanomechanical analysis is under the ISO standardization, and I'm the convener of this field. And actually, the nanomechanics calculation using a JKR 2-point method is now the draft version of ISO standardization document. So you will see soon this document within a year or so. So please enjoy. Okay, but anyway, using this type of analysis, you can perform a nanomechanical analysis on various type of polymeric material. This is one example. This is the SBR styrene butadiene rubber and the butadiene rubber. Both are rubber, but immiscible blend samples. Then you can see the JKR the theoretical curve nicely reproduce the experimental curves. And as you can see, in the left hand side, the modulus mapping is like obtainable. And then, as is seen in the histogram, such a small difference between the two the domains can be distinguished. So nanomechanical mapping is really the powerful tool. Okay, although as I mentioned, this is only for the Young's modulus measurement, so it's just a static measurement, and no information of viscoelasticity is obtained. But if you work on the static modes, still you can do some viscoelastic measurement. This is one example. So in this case, I use the IR vulcanizate. The cross-linking is performed by sulfur. Then, by adjusting the sulfur contents, you can see some heterogeneous cross-linking situations. The left-hand side image is a Young's modulus map. Then you can see some the contrast, the green and the orange colors. And then this just tells us the stiffness difference, the modulus differences. But the question is how this difference comes from. Then the right-hand side image is energy dissipation. The question is how we analyze it. So the slides tell you the result, my idea. So this side, the JKR fit nicely reproduce the curve. So which means that this portion is purely elastic. But this one, some deviation between the theoretical curve and the experimental curve is visible, and this means the JKR analysis is not perfect. Then the area corresponds to some deviation from the elastic response. So we may be able to think about that this is energy dissipation caused by viscoelastic interactions. Then this was visualized as the right hand image, which I call energy dissipation. Then now we can have the correlation between the elastic, the response and the viscosity responses. Then what I found is a purely elastic region is, as I mentioned, the energy dissipation is almost zero, but the softer portions are viscoelastic, so energy dissipation have some value. So in this way, you can perform some viscoelastic measurement even using the static measurement. But we want to go beyond this type of measurement. This is what we want to talk about today. Another the example of the static nanomechanics is on field samples. I mean that some nanoparticles embedded in the polymeric materials. okay, sorry. Okay, so this image is the rubber, but it contains the lot of amount of the nanoparticles. Then this is once again the Young's modulus map. So the rubbery region has a 2 megapascal level, the modulus is, and the fillers, yes, of course, very hard, but we can see some the green regions, which is an interfacial region the Young's modulus is several times higher than the real matrix. So this increase is the result due to the strong interaction between filler and the robots. Now I'm collaborating for tire companies in Japan, so which means that this type of technique is really important in industry. But the industrial people request me to further extend this type of technique to not only the static measurement but the dynamic measurement, because in their daily life they use the dynamic moduluses like the storage modulus or the loss modulus or loss tangent, as in this picture. This is one example. The effect this guy, the very famous in the field of the rubber industry, did a very interesting measurement. So he prepared the 3 different the fillers. The surface, the difference is the surface treatment for the fillers. Then the macroscopic properties changes in this the figure. So the interfacial interaction can change the macroscopic the properties. So the question is how the interfacial region is different. This is the long-lasting question for the rubber industrial peoples. So I talk about how we can visualize the interfacial region in terms of viscoelastic properties in my slides. Okay, but before going, first of all, I will talk about a little bit about the viscoelasticity. So now you can see two the rubber balls. One is nicely bouncing, but the other one is non-bouncing. So the actually material are different. Both are rubber, but the bouncing ball has the very low TG, like minus 50 to minus 100 degrees C, but non-bouncing ball, the glass transition temperature TG near room temperature. Then the question is in this non-bouncing ball, why this non-bouncing ball non-bounce? I mean that we give some the potential energy to this rubber, but it totally dissipated. So where this energy goes, energy is dissipated. So this type of discussion can be made with a viscoelastic measurement. Usually, we perform bulk dynamic mechanical analyzer to analyze the viscoelastic properties. So as in this the slide. So in case of bulk DMA, we give a sinusoidal oscillation to the sample and observe the responses. But question is, the applicable frequency range is usually like 2 orders of magnitude, and which cannot fully cover the responses from the polymeric material. So instead, you need to change the temperature, like in this figure. Then although I will not go into the detail of this theory, there is a theory to shift the all of the data to left-hand side or right-hand side. I mean the low frequency region and high frequency regions using this equation, and then to obtain this type of master curve. So based on this theory, high temperature responses is related to low frequency measurement, and the low temperature measurement goes to high frequencies. so that finally we get this type of nice the frequency dependent measure the curve, which give us the insight of the polymeric materials. Okay. Now we have developed how reproduce such kind of DMA measurement using AFM. First, the trial was appeared in macromolecules in 2013 or 14, and also the way how to realize this measurement is depicted in this cartoon movie. So we add the conventional force volume measurement with sinusoidal oscillations with a frequency sweep. In this specific case, we use a tiny piezo underneath the specimen, and the frequency measurement is of resonant conditions. And then because this sinusoidal oscillation is performed during the contact, so adhesive hysteresis nicely minimized. So this is the idea. Then more detailed discussion is written in this slide, but the next speaker, will discuss more about the theoretical treatment of that. So I will skip on this. And now I show you the first example on using this type of technique. Once again, the sample is SBR-IR immiscible blend sample. Then in right hand side, you can see the frequency dependent changes of the images of these immiscible blend samples, starting from 10 Hz and 20 kHz. And left hand side, this is a summary of the frequency dependence. Then the blue indicates the storage modulus, and the red indicates the loss tangent. Then this open symbols is for the bulk measurement. As I mentioned, bulk measurement only have 2 decades the frequencies. Then you need to change the temperature. But our AFM technique have a very wide frequency nature. So in this specific case, we could perform 4 decade 4 order of magnitude of frequency changes at room temperature. And more importantly, the data is nicely correspond to each other to the bulk properties. So this technique is really quantitative. Then quite recently, we applied this technique to field robust systems, which appeared in macromolecules. Once again, this is the lava sample. Then the silica nanoparticles is embedded in the lava matrix. Left-hand side image is the static modulus map, and the right-hand side data is a new data, which is a loss tangent. Then, by the way, I show you one slide, which is very important. You can change the amplitude of a sinusoidal oscillation like this. Then, if you restrict the sample deformation at lower values, then the response is ellipsoidal. So, which means the measurement region is a linear region. But if you increase the sample the deformation to higher values, actually this portion, first of all, the value is constant, but start to decrease. Other frequencies also show similar trend. Then the response is no more ellipsoidal. So the shape is little bit deformed, which indicates the non-linearity is start to be observed. So then the phenomena become more complicated. So you have to be very careful in your measurement to bring your experimental condition to a lower the small amplitude. Maybe Bede will also explain some detail on that. But anyway, this is the main result on this field SBR samples. So we change the frequency, and also we get the storage modulus and the loss modulus and loss tangent. Yeah, with different frequencies. Then, as you can see, in the color change, the responses are changing with the frequencies. This is a summary of these results. Yeah, once again, this open symbols is coming from bulk DMA, and the other data, this data or this data, or this data is by nano DMA measurement. So the very nice coincidence between the nanoscale measurement and macroscopic measurement is once again evident. And then in this specific case, we change the temperature. Then this is for the higher temperature, and this is for the lower temperatures. And the very interestingly, macroscopic measurement and the nanoscopic measurement coincide nicely. But this is the data, the average over average data over all of the samples. But our technique have spatial resolution. So we divide the responses from the matrix regions data and interfacial data. So matrix and interface give different the responses. And very interestingly, macroscopic data comes in between. So by thinking of some new the calculation method, maybe from the nanoscopic data, we may be able to predict the macroscopic data. This is ongoing, the project. Another example is kind of very big trial to observe to check the validity of time temperature superposition principle. So the system is very simple. Once again, this is rubber vulcanizates, cross-link samples, but no filler is added. Then the left-hand side image is storage modulus, and right-hand side image is loss tangent. And today, I will just focusing on the loss tangent. So converting this image into the histogram, and then I discuss average value and the standard deviation, so width of this peak. Result is this. So this time I change the frequency for 2 order and change the temperature. Then we shifted the values, the high temperature data to low frequencies, and the low temperature data to high frequencies. Then to get the one nice the curve, master curve. The point is the how much you shift each data. I based on the shift factor obtained from macroscopic measurement. So actually, I can superimpose the macroscopic data like this. So nano and macro once again nicely coincide each other, which means time temperature superposition principle holds even at the nanoscale. Yeah, it's good, but not so interesting. But more interesting feature was observed by looking at more detail. Please have a look at this side. The average value itself now agree to each other, but please look at the standard deviations, which is now shown as an error. Then at the high temperature data, the standard deviation is small, but by decreasing temperature, the standard deviation increases. What does it mean? Yes, we'd better to have a look at the image itself. So here, the two images, although they are not same location, unfortunately, but they're from the same sample. Okay, so the left-hand side image is the 1 micrometer scale loss tangent data measured at the room temperature and higher frequencies. And the resultant reduced frequency is about 1.1 kilohertz. Then, right-hand side image is the obtained at the decreased temperature, 14 degrees C, and lower frequencies, in order to get the almost same reduced frequency of 1.3 kilohertz. So, as I mentioned, then these two data have almost same the average value of near 1. But the standard deviation with this is totally different, and the appearance in an image is different. Length scales are different, and some the values the deviated from the center values are also different. So this tells us that the very important message. So if the value is average over, then the TTS is okay. But if you look at the nanoscale, then TTS can be breakdown. Okay. So this is further discussion of this phenomenon. So this red curve is the data from all over the areas. But if you have a point-by-point measurement, then the curves are deviated from this average values. Actually, the peak values are different. What does it mean? Yes, glass transition occurs heterogeneously. In other words, glass transition temperature are dependent on the place by places. So the polymer segmental motion are not so homogeneous, very, very heterogeneous. Okay. Finally, I show you some slides during the installation of this nano-DMA to Tokyo Tech. The BID came to Japan and installed a new machine. He's my student anyway. Then we did a kind of preliminary measurement. Yeah. By the way, this fast force volume is also a very new technique, which I start to use. So this is preliminary result, and I did the force distance curve measurement on non-bouncing ball. Then, by changing the frequencies, then we observe a totally different the force distance curves. Then, from these curves, we can calculate the JKR static moduluses. And as you can see here, but JKR result and the experimental curve are deviated due to viscoelastic responses. So the macroscopic data and this data have some deviations, which we will think about in the future, how you can predict from the single force curves the macroscopic data. Please wait. But anyway, we did the nano-DMA on this non-bouncing ball, and this is the data. So this image is peak force QNM, the DMT modulus data. Then on this region, here is the fillers, but here is the matrix region. Then we did a nano-DMA measurement, and then this is the storage modulus, and this is loss modulus, and this is loss tangent. We still have some deviation from the macroscopic data and the nanoscopic data, but this is preliminary result. But then after repeating this measurement, we maybe solve quite nicely. Then I think this nano-DMA is really, really powerful too. So the detail of nano-DMA will be explained by BID. So I will finish my presentation here. Thank you very much for listening. That's all.
Thanks for the great presentation, Professor Nakajima. This is Beat Pittenger, and I'll be discussing the Bruker implementation of AFM-based nano-DMA and some of the experiments we have been doing to validate the technique. Perhaps before we get into that, I should mention another Bruker technique, peak force Q&M. Peak force Q&M is a great solution for elastic modulus mapping. It's fast, repeatable, and high resolution. It's able to collect the adhesion simultaneously with the modulus, and you don't need to use reference samples. So the question is, could we just add viscoelastic channels to peak force Q&M? Well, really we can't do that, and it comes down to two things. Firstly, the frequencies are just too high in peak force Q&M. And secondly, we're lacking a realistic model to quantify the key viscoelastic properties of storage modulus, loss modulus, and loss tangent. In imaging modes like tapping mode or peak force tapping, which peak force Q&M is based on, you typically want to go as fast as possible and minimize the time in contact with the surface. This is in conflict with the needs of rheologists who want spectra that span low frequencies. This need for speed leads you to probing the sample impulsively, breaking the tip sample contact in every cycle. Measurement is not linear, making the modeling difficult. And the nominal frequency is not the only frequency, so the frequency is not well defined, and this prevents direct comparison with bulk DMA. In tapping mode, things have additional complications. There's only one frequency involved, the resonant frequency of the cantilever, and it's kind of a ridiculous frequency. It's like 100,000 times too large. Also, load and adhesion are really non-trivial to extract from the data, so it makes it very difficult to do good modeling. When we started talking to collaborators like Ken, we realized that we needed a different approach, one that provided a well-defined rheological frequencies as a perturbation to a carefully controlled preload. And at the time, Professor Nakajima's team had already published this 2013 macromolecules paper, where the multimode was used to demonstrate the key features of this new method. So we started out by looking at this basic method and making sure we controlled the preload during the approach, and then while we're in contact, modulating at a well-defined rheological frequency with a very low amplitude. That gives us a small perturbation in force and keeps us in the linear regime of the measurement. It also gives us the ability to collect both spectra or single frequencies and cover this low frequency range, which is important. And then finally, during the retract, we fit the retract curve with contact mechanics, which includes adhesion, like JKR, to obtain the contact radius, and that allows us to get the storage and loss modulus. This has two key advantages. The first advantage, the adhesion is largely separated from the loss tangent, and I'm going to refer to loss tangent as tan delta sometimes in this presentation. So you'll hear me say tan delta, loss tangent. I just mean the same thing in both cases, okay? Anyway, the adhesion is separated from the loss tangent because the tip is not going in and out of contact during the modulation. So dissipation is no longer strongly coupled to adhesion as it is in tapping mode and peak force tapping. These maps of polystyrene PMMA block copolymer demonstrate that despite very large adhesion and contrast in adhesion, 6 to 10 nanonewtons is what we're looking at here, the loss tangent really lacks any significant variation. On the other hand, there is some contrast in the storage modulus, and that's expected. That correlates to the roughly 20 nanometer domains in the material. So that's one of the main benefits of this method of doing the modulation while you're in contact. The other one is that the analysis is relatively simple, and you can get direct access to the storage stiffness, loss stiffness, and loss tangent. As mentioned earlier, we're going to apply a sinusoidal motion to either the tip or the sample. It's going to be going to a Z piezo. And we will measure the amplitude and phase of the Z piezo motion and of the deflection response, okay? If we have that information, we have this amplitude ratio and we have a phase shift, then we can pretty quickly get out this complex stiffness, which is just the force divided by the deformation. And we can separate it into a real part called the storage stiffness and an imaginary part called the loss stiffness. Now if I take the ratio of those two, then I get directly the loss tangent, or tan delta. And you'll notice that this doesn't depend on anything except for the amplitude ratio and the phase shift. So we have a direct measure of the amplitude, or of the loss tangent. So if we want to collect spectra with low frequencies and not just limit ourselves to a single frequency, the best way to do that is to use a script or a series of measurements that can all be optimized to their tasks. In this data set, we approach the surface and we come into contact, so that's one segment right there, the approach. And then we do a stress relaxation segment where we just hold the force constant. And then we apply various different modulation frequencies. And then we retract the tip from the sample, and so we can do our contact radius fit. So every one of these segments has a duration that's optimized. They can be randomly organized in the script if you want to. You can basically control the duration, the frequency, the sample rate, et cetera, for every one of those segments. Now, if you would like to get the moduli, in other words, the storage and loss modulus from the storage and loss stiffness, then we also need a contact mechanics model like JKR to estimate the contact radius. So at the end of the script, it's very easy to use this retract section to get the contact radius at the very end of the script. But as you can see from this plot, my contact radius actually varies during the script. So over time, my contact radius usually increases. So if I want to get all of the storage moduli and loss moduli at different frequencies, I need to know what the contact radius is at each of those times during the evolution of the contact. So that's kind of an intrinsic difficulty that comes with making accurate viscoelastic measurements with indentation type methods. The samples that exhibit a significant viscoelastic response also have relaxation under load. And this relaxation leads to the changes in the contact radius during the measurement. Now, AFM is kind of relatively new to doing this type of measurement, but our friends at Hysotron, who have been making nanoindenters for quite some time, have been working with this for quite a while, and they helped us to develop some strategies to deal with this sample creep. One of the strategies is just to add a relaxation segment, which I mentioned earlier, but another is to track the variation in contact radius. And you can do that by adding in reference segments. Each of the segments have the same frequency, and they're randomly oriented through, or they're dispersed through the measurement. because we can assume that the storage modulus is constant during the measurement, that allows us to, or at a given frequency, that allows us to actually calculate out the contact radius, because we can measure these stiffnesses. So we can get a estimate of what the contact radius is over time, and then interpolate to calculate out the storage moduli everywhere during the script. Now that seems kind of complicated, and so what we did is we kind of set up having the software a ramp script generator. And that's because you typically want a lot of segments for your detailed spectrum, so it would be tedious to set them up by adding them one at a time. So we developed this ramp script editor or generator, and it automatically creates a ramp script given 5 key parameters, essentially the range over which the frequencies are going to be dispersed and how many steps you'd like to take, the preload, and the force set point. These are pretty much what a DMA user would expect. The frequencies, the preload, and the amplitude. Now, if you do want to get into the details of how the measurement's done, you can get to these advanced parameters. So that allows you to control the frequency distribution, like whether it's going to be a log step or shuffled frequencies or what. You can also control the reference segments, how many there will be, and what frequency you're going to use, relaxation duration, all kinds of things about the ramp, et cetera, et cetera. And then finally, if this isn't detailed enough for you, you can actually go to the next level, which is to directly edit segment by segment the ramp script. So then you can adjust any of the controls on each segment. Now the question is, now that we've done all this, can we actually match the bulk DMA? Well, we compared our results between the AFM-nDMA and a bulk or measurement, and also a nano indenter. And so the blue circles here are our AFM-nDMA results. The top is the storage modulus, and the bottom is the loss modulus. Now, the Heisotron is actually in blue crosses right here on top. And then the bulk DMA is the green lines. So you have a green dashed line and a green solid line for the loss modulus. And you'll notice that both of those end at about 300 hertz. But we can go a little higher in frequency with the AFM. Actually, we can get up to about 20 kilohertz, all with a single script. So that's going to be about, I think it's about 5 orders of magnitude. Basically, you can notice that actually our storage modulus is changing quite a bit here. So frequency really does matter in this mechanical property measurement on this sample. And so really when we talk about modulus, storage modulus, or Young's modulus also, we should be talking about the frequency and temperature at which it's measured in order to actually be quantified, or to quantify that measurement. We also did test this across different labs and operators. So you have the orange triangles here. These are from a collaborator in a different lab on a different continent with a different probe. We're using optimized probes. These are some of the tip shapes that we use. And they're pre-calibrated, so we just scan the box, and that gives us the key calibration parameters. So we can be quantitative. And the other thing Professor Nakajima already described was the time-temperature superposition. And very commonly, rheologists like to generate a master curve that has a very wide range of frequencies. And they do this from a series of narrow spectra collected at different temperatures. And Professor Nakajima already showed you some results, but I wanted to go over this one more time and show you a little bit more data. Essentially, near the glass transition, raising the temperature is equivalent to lowering the frequency, and vice versa. Now, so you can construct this master curve just by shifting these little spectra, and then basically you can actually analyze the shift factors by either a WLF model or an Arrhenius model, and that gives you a couple of parameters. The Arrhenius one gives you an activation energy, so you can do a comparison just over one parameter instead of comparing over the whole spectra if you want to compare with, say, bulk. Okay. For bulk, this works quite nicely, but as Professor Nakajima showed, things are different at the nanoscale. So to tackle this with our system, we developed some new hardware, actually. For variable temperature measurements, a new low drift heater was developed to optimize the accuracy of collocation of the spectra and images, and to reduce the time required to stabilize when changing the temperature. As you can see, it attaches to the back of the dimension icon motorized stage. With the new heater, the stabilization time is now dominated by the time required for sample relaxation. So if there's stress in the sample, it may take a little while to work that out. When higher frequencies are needed, we can use this a high frequency actuator here in green, which can extend the range of the spectra from 300 hertz up to about 20 kilohertz at room temperature. And that gives you about 5 orders of magnitude in frequency without needing to change the temperature. So can we do time temperature superposition with our AFM-nDMA data? Well, we need a bunch of spectra at different temperatures. So here's some typical spectra on a fluorinated ethylene propylene sample. And it qualitatively shows kind of what we're expecting from the behavior. We have a glass transition happening with a loss tangent peak here. And when we go to higher temperatures, or when we go to higher frequencies, the peak shifts to higher temperatures, and so that's the expected frequency dependence. But how well does that actually match the bulk? Well, it looks pretty good, actually. So our green points are the bulk DMA here, looking at the loss tangent. And the blue is the AFM-nDMA. And so we have a spectra that's covering around 20 decades of frequency now, that's based on measurements that were done between 0.1 hertz and 300 hertz. And so we shifted a bunch of those spectra, and these are the log base 10 of the shift factor. And so you can see that if we do the same analysis for Arrhenius on both the bulk DMA measurements and the AFM measurements, then we get very close to the same activation energy. So it works pretty well for bulk measurements. And it looks like, so it really looks like we can do bulk measurements pretty well. We have the PDMS example, we have the fluorinated ethylene propylene example, but we really want to do heterogeneous samples. So what if we do something like this 4-component polymer blend? Well, We typically approach this by first collecting peak force Q&M images. And we can do mapping with the DMT modulus in peak force Q&M. And then that can show us what areas are interesting to look at. And this image would maybe a 512 by 512 image. It might take about 10 minutes. And then we typically switch over and we might do a single frequency AFM-nDMA map. This image is about 70 by 70 and it takes about 30 minutes. And so we get the storage modulus at 100 hertz, which happened to be our modulation frequency, for each pixel in the map. Then we would go ahead and we would do spectra at selected points. Now these spectra could take a few minutes depending on what the minimum frequency is, really. And these go down to pretty low frequencies, so these are more than 3 minutes per spectra. But you can see quickly that the COC, polypropylene, LLDPE, and the elastomer all have very different frequency response. And actually, there may be a crossover between the polypropylene and the LLDPE at high frequencies, where it looks like they might be coming together. If we look at another polymer blend, which just has polypropylene and COC in it, or cyclic olefin copolymer, then we can actually see a crossover that can happen. But in this case, instead of doing the measurements as a function of frequency, we do them as a function of temperature. So we have here on the top row maps, force volume maps again, of storage modulus at different temperatures. And then in and we also have a plot of the storage modulus of the two components as a function of temperature. So with in the storage modulus, essentially they start out at the same value, the two components, and then the polypropylene quickly decreases in stiff storage modulus. And eventually at 175, then the COC really gets softer as well. But you stay that way pretty much the whole time. Now with the loss tangent, what happens is the polypropylene starts out softer or lower in loss tangent than the COC. And then as the temperature increases, they actually match pretty well. And then we have a contrast inversion where the COC now has significantly larger loss tangent. And so at that point, the sample is almost like a sponge full of liquid. It's very, very lossy, and it really damps the material significantly, at almost 0.3 for the loss tangent. Now, at 170 C, you can see this ring around the COC component. It's possible that this is due to the presence of an interphase, but we have further work to do to confirm that we're not seeing an artifact from the topography, since there is a step here in terms of topography. But that is actually kind of possibly an interphase, and the pixel size here is about 50 nanometers, so it's kind of on the length scale that you might expect. In summary, the AFM is a natural tool for doing nanomechanical measurements, but traditional imaging modes for AFM are not well suited to studying viscoelastic properties of materials due to the nonlinearity of the measurements and the frequency mismatch when comparing to bulk DMA. AFM-nDMA solves these issues by doing the measurements at the same frequencies as the bulk DMA, and by using a preload with a small perturbation in force to keep the measurement linear. not all samples are as easy as a PDMS sample, but real-world samples have also generally had a reasonable agreement with bulk DMA. Since AFM-nDMA works at well-defined frequencies and temperatures, it is possible to generate the master curves using time-temperature superposition and to do an Arrhenius or WLF analysis on the resulting shift factors. And so far, it seems like the numbers are pretty reasonable in terms of agreement. Finally, Professor Nakajima's results show that there are differences between bulk and nanoscale viscoelastic behavior. AFM brings the possibility of doing these measurements with a resolution of better than 50 nanometers to understand the differences and to explore where they're coming from. Thank you.
Okay, well, this is Thomas here again. I want to thank both Beat and Ken for their great presentations here. We have a number of questions in, so give me just a few seconds here to get my bearings, and we will try to answer a few of your questions right away. And then, as I mentioned in the beginning, follow up for further questions with email. So if you have any questions, don't hesitate to still add them in the question dialog box. I definitely want to capture them. Let me see. Yeah, so there's actually, I see there are several questions that are maybe questions mainly for Ken, where Ken, you showed, you had this really interesting result where you showed the heterogeneity, and the TG, for instance, varied with location. You showed these two images that had different level of contrast, even though they were at a similar reduced frequency. There are several questions on that here. One, what is the length scale of these microphases you see? Two, what do you think is the physical origin of the variation? And three, can you say anything about how this helps optimize the material?
Okay, thank you for the questions. Now, I can show once again my presentation file. Just one minute. Oops. Oops. No. Oh yes. So here is the once again the picture. Yes. Because the size of the scan size is 1 micrometer. So for this one, it's about a few thousands of nanometers, like 30, 40 nanometers. The heterogeneity is observed. But the lower, the case of high temperature data, the length scale is much larger, and which is nothing to do with the any type of the molecular level heterogeneous. It's not the molecular level size. So currently I cannot tell what's the origin of that. But as I mentioned before, the cross-linking density fluctuation also exists, whose size is about the 30 nanometer. So for this, actually this right hand side data is near the glass transition temperatures. So which reflects the cross-linking density fluctuations. But the higher temperatures, we still have, this is in Lavalier region, but we still have heterogeneity. Currently I cannot tell why. And what is another question?
Yeah, the third question was, can you say how this might help optimize the macroscopic properties?
Aha. Oh yeah, it's a good idea. It's question. Actually, I was working on, as I mentioned, I work with the industrial people. Then this type of heterogeneity coming from the viscous nature of Lavalier materials. So if you use this sample as material, then the highly energy dissipative region still remains. So if you want to use this as a tie application, this is not good thing. So by changing the cross-linking manner, the procedures, then we actually were successful to reduce this type of heterogeneity to achieve the high fuel efficiency tires. So this means that by changing the cross-linking density, you can change the properties.
Okay. Well, thank you very much. We have another question here. It's a question about the probes. The question is, how do you image the AFM probes? I recall Beat did show an image of the AFM probe, and I could say to that, we do use special pre-calibrated probes for these measurements, which have a vibrometer calibrated cantilever spring constant and also a specially manufactured tip, which is made to be very consistently cone-shaped, and we do individually SEM image these probes actually to determine radius on an individual probe basis as well. I don't know if Beat wanted to say anything else there.
Yeah, so the right now we're making two different versions of these. One has a 30 nanometer radius nominally, and the other one has a radius of 125 nanometers. And they are individually measured in the scanning electron microscope. Normally, you would have a hard time measuring an AFM tip and radius with an SEM due to the apex being so sharp. But when they're over 30 nanometers, then really this isn't such a problem, and we can get an accurate measurement of the tip radius.
Okay, good. Another question here, which may be one for Beat. It refers to the FEP data, where it says, Beat, you showed a master curve with frequencies up to the 10 to the 18 hertz or something. So the question is, how did you measure at that frequency?
Right. So in that case, again, we did not actually measure at 10 to the 18. What we did is instead we measured over a range of temperatures and a much narrower frequency range. The frequency range that we actually measured in was 0.1 hertz up to 300 hertz. And so the at room temperature, at elevated temperature, at room temperature and the highest frequency, the 300, when it's translated, we are able to get to that frequency.
Okay, thanks. Yes, and actually another question that could be maybe interesting for both presenters. From your experience, what kind of sample preparation is needed for this technique? Maybe Abhi, do you want to start and then give Ken a chance as well?
Sure. So it depends a little bit on exactly what frequency you want to do the measurement at and what temperature. If you're working with higher temperatures, you typically want to have a very thin sample because your sample will take a long time to stabilize because of the stress of the sample. So if you're working with the high frequency actuator, then you also want a very small sample because of the mass of the sample. You don't want that to contribute. However, if you're working at room temperature and you're working at, say, under 300 hertz, then really you can work with most samples. It doesn't matter how big they are. For the small samples, what I'm referring to there is something like a cryosection or a thin film or just a small piece of material. For example, in the case of the PDMS, the samples were just small pieces of PDMS that were around 10 microns thick, I believe.
Ken, would you have any advice or any comment further on sample preparation for successful measurements?
Beat made a very good answer, and nothing to be added.
Okay, good. Thank you. Oh yeah, let's see.
Yeah.
Thank you. We are already well over the hour. Let me maybe just one more here. Maybe it could be a question for both as well. Actually, there are two more questions that maybe you want to. One is how do you know that you're in the linear regime? Maybe let's deal with this one first.
Okay. Well, actually, Ken showed a very nice slide there about how you might do that. But basically, there are two ways that are also they've been used by the bulk DMA community over the years. One of them is to look for a deviation of your sinusoidal response from a pure sinusoid. So if you see any deviation there, then that is reflected in what's called a Lissajous plot, which is what Ken showed. Maybe I can give Ken control again here. And then the other way would be to look at what happens to one of your property channels as you change the amplitude. So if you have small amplitudes, then you typically have a linear response, but as you get up to a large enough amplitude, then the response is no longer linear. And then the amplitude would, or the property typically drops off at that point.
Yeah. And maybe to the so there is this, and one further question, maybe also interesting for both presenters. What kind of spatial resolution do you think you can achieve with this technique?
So the highest resolution I have done is probably that black copolymer data I showed earlier, where the resolution was around 20 nanometers. However, we have not done any measurements with sharp tips. Basically, the probes we're using are 30 nanometer or bigger tip radius. So it doesn't seem like, I mean, we've really tried to push it to really very high resolution. Ken, do you have any comment about that?
Yeah, it's really depending on the contact area. So depending on the material and the properties, if soft samples, then if sample deformation is big, then the contact area also increases. So in order to, in this case, you need to restrict the maximum force during this nano DMA measurement must be very small. But but anyway, in my experience, the current stage, the spatial resolution of 20 or 30 nanometer.
Okay.
Very good. Thank you both, and I want to thank again both you, Ken and Beat, for this great presentation today, and thank the audience for their attention. We're well over the hour, so we'll wrap it up now and follow up on further questions by email. And so thank you, everybody, and hope to see you again soon on our next Bruker AFM webinar. Okay, thank you. Bye-bye.